Okay, folks, it's good to see you back. So last time we started our discussion of frictional losses. So this is going to be a really important topic in this course. It's something we're going to be using really throughout the remainder of the course. Frictional losses will generally be the largest source of head losses that we'll be dealing with. We talked about two different methods for computing frictional losses that are used together. So the first is the Darcy-Weisbach model for computing frictional losses. This gives us the head loss over a pipe of some length delta x, given the diameter, the velocity in the pipe, along with some friction factor. And to compute this friction factor, we introduced another equation, the Colebrook-White equation. So this is used to compute that friction factor F. Note that this Colebrook-White equation is an implicit equation, so this is not something that can be solved in closed form. So on Thursday and Tuesday of last week, we showed how we could compute the friction factor iteratively using the solver functionality in Excel, and we went through a couple examples of how to do that. Are there any questions on these two models for frictional losses? All right, so we covered these kind of basic methods. These are kind of generally the most theoretically correct model for computing frictional losses that we can get. However, as I noted, sometimes computing friction factors using Darcy-Weisbach and Colebrook-White can be inconvenient because specifically we have to solve for the friction factor iteratively, and that can pose issues. It can often be less convenient than we would like. So there are a couple alternative friction loss formulations that I want to introduce today. So these are more empirical approaches that we'll be using to make our lives easier. They're not only easier to compute, but these are also widely used within the water industry. And so these are all models that you should know. So the first is the Swamee-Jain approximation to the Colebrook-White friction factor. So this is going to be used with the Darcy-Weisbach equation in place of the Colebrook-White equation for solving the friction factor. The second model is the Chezy-Manning equation. So this is widely used for computing frictional losses in open channel flow. It's also applicable for pipe flow as well. So we'll be talking about the Chezy-Manning model. And then finally, the Hazen-Williams equation. This is widely used within water distribution for computing frictional losses in pipes. So today I'll introduce these three empirical models for computing frictional losses. We'll do a couple examples and compare the results between these three models. And then towards the end of lecture today, I'll start getting into minor losses, which are caused by changes in the geometry and flow paths of flow. This is something you probably covered in fluid mechanics. We're going to review it today, talk about different types of minor losses in pressurized pipe systems. So I quickly want to recap how we derived the Darcy-Weisbach equation. So this came from basically coming up with two independent formulations for the mean shear stress in a pipe and then equating them. So the first expression for our mean shear stress comes from the definition of the friction slope. We had that the mean shear stress was equal to the acceleration due to gravity times the density times the hydraulic radius r times the friction slope. By the way, what is the hydraulic radius r defined as? Very good. So it's the cross-sectional area divided by the wetted perimeter. So this is an important definition to remember. Cross-sectional area on top, wetted perimeter on the bottom. And this is called the hydraulic radius. Note that for circular pressurized pipes, the wetted perimeter will always just be equal to the circumference of your pipe. So we had one expression for the mean shear stress that was given by the definition of the friction slope. We also had another definition of the mean shear stress that came from Newton's drag law, which is something you might have learned in Physics 101. So we have from Newton's drag law that the mean shear stress acting on an object submerged in some fluid is equal to some drag coefficient CF times the density of the fluid times the velocity of the fluid squared divided by 2g. And if we equated these two expressions, we ended up with the following. We have the acceleration due to gravity times the density times the hydraulic radius times the friction slope is equal to the drag coefficient times the density times u squared over 2g. And we can rearrange this expression for the friction slope. We have that the friction slope is equal to, if we just divide through by the hydraulic radius times the density times the acceleration due to gravity, we have that the friction slope is equal to some drag coefficient CF times u squared divided by 2 times g times r. And then if we have the friction slope, how can we compute the head loss over some distance delta x due to friction? Multiplied by delta x. Very good. So if we take this entire expression and we multiply both sides by delta x, this will give us the head loss. So we have that the head loss is equal to some drag coefficient CF times delta x divided by the hydraulic radius times the velocity squared divided by 2g. So for circular pipe, we were able to simplify this general expression for the frictional losses. For circular pipe, we have that the hydraulic radius is equal to the cross-sectional area divided by the wetted perimeter. So the cross-sectional area is given by pi times the diameter squared divided by 4. That's from our formula. Yes. Actually, you know what? I think it's because there's no g in Newton's drag law. I think I'm just so used to writing 2g in the denominator. I'm pretty sure that there's no g in the denominator of Newton's drag law. If someone wants to verify that, that's correct. Yeah. Yeah. Thank you for pointing that out. Okay, so for circular pipe, we have that the hydraulic radius is the cross-sectional area divided by the wetted perimeter. So the cross-sectional area is pi times d squared divided by 4. The wetted perimeter will be equal to pi times the diameter. So this reduces to d over 4. And thus we have for circular pipe, the head loss is equal to 4 times this drag coefficient times delta x divided by d times u squared over 2g. So what we did for Darcy-Weisbach was we took this expression 4 times the drag coefficient, and we just lumped these together into a single coefficient f that we called the friction factor. That's where Darcy-Weisbach comes from. Basically, all of the other empirical models that we'll be coming up with today are just different ways of specifying this drag coefficient here, or this friction factor coefficient here. So let's take our expression for the head loss. So we have that the head loss is equal to CF times delta x divided by r. So this is the general case. We have, maybe a non-circular hydraulic geometry times u squared divided by 2g. We can re-express this in terms of the discharge. We have that the velocity is equal to the discharge divided by the area. So the velocity squared will be the discharge squared divided by the cross-sectional area squared. So we can rewrite our head loss in terms of the discharge. This will be CF, our drag coefficient, times delta x divided by r divided by the cross-sectional area squared times the quantity q squared divided by 2g. And we can also rewrite the friction loss equation with the discharge as the dependent variable. So all I'm going to do is just going to rearrange this with q on the left-hand side. This is another way that we'll be looking at this equation. So we can write the friction loss with U or Q as the dependent variable. We take this first expression here and just rearrange it for U on the left-hand side. We'll get that U is equal to the square root of 2G divided by our drag coefficient times the square root of the hydraulic radius times the friction slope. And if we multiply this entire thing by the cross-sectional area, what do we get? We multiply this velocity by the cross-sectional area, Q. We get that Q is equal to cross-sectional area times the square root of 2G divided by our drag coefficient times the square root of the hydraulic radius times the friction factor. So what we can do again is we can just take this entire term here and we can group this together into some coefficient C. And if we do that, we end up with this general form for the discharge. We get that the discharge is equal to this coefficient C times cross-sectional area times the square root of hydraulic radius times the friction factor. So we'll be dealing with both forms of these frictional loss equations, one with the head loss as the dependent variable, one with the discharge as the dependent variable. I just want to get you accustomed to looking at both forms right now. And basically all of the different frictional loss models we'll be looking at are just different ways of specifying either this C coefficient here or this CF coefficient up here. But you can think of all of these as basically being the same kind of relation, except with different values for this, or different functions for this C coefficient. So are there any questions so far? Yes. Yeah, so I took this equation here and I just rearranged for the velocity.
Where did delta x go?
So what's the relationship between the friction slope and the head loss?
The distance.
Right, so I divided by the distance delta x to get the friction slope instead of the head loss.
Let me get the under the in terms of discharge, did you just multiply by area squared?
Yes, so I divided by area squared. Because U squared is equal to Q squared divided by A squared. Good questions. Any more questions on our general framework for thinking about frictional losses? Basically, it's going to be some form of this or some form of this, no matter which loss equation we're looking at. Okay, so let's start with the most familiar case. We're going to look at the Swamee-Jain approximation. So this is an approximation to the Colebrook-White friction factor that's used along with the Darcy-Weisbach frictional loss model. So this is used with Darcy-Weisbach. And you can essentially think of it as a drop-in replacement for Colebrook-White. So this replaces Colebrook-White. It's an approximation to the Colebrook-White equation for computing the friction factor. And it's going to make your life a lot easier. So from the Swamee-Jain approximation, we have that our friction factor F that's used with Darcy-Weisbach is equal to 0.25 divided by the log 10 squared of E divided by D divided by 3.7 plus 5.74 divided by the Reynolds number to the 0.9 power. So let's just make sure we define all these terms here. This is our friction factor. It's the exact same friction factor we've been using. We use it with the Darcy-Weisbach equation. This E here, this is the roughness height. The D is the diameter. And this term here is the Reynolds number. So it's similar to Kullback-White, except it gives us an explicit expression for the friction factor F. So it will make solving problems that you've been using Kullback-White to previously solve, it'll make them much easier. So this is a good approximation for Kullback-White. It's within 1% of the true value under the following conditions. So first, if the ratio of the roughness height to the diameter is between 10 to the negative 6 and 10 to the negative 2, and the Reynolds number is between 5,000, so that's 5 times 10 to the third, and 10 to the 8th, so that's about 100 million. So it's valid for a pretty wide range of roughnesses and Reynolds numbers. So for almost all of the for almost all of the problems that we'll be looking at in class, this is a good approximation to Kullback-White. So unless I say otherwise, you can use this equation for computing the friction factor in place of Kullback-White. Yes?
What is that 2 about the log 10?
So that means you can think about it like this. Take the log 10 of this expression here and then square the entire thing. So I'll just write it like this to be explicit. Yes. Just because when this approximation was derived, it was, fitted to the Kullback-White function for a range of typical values that you'd find in water distribution and other piping systems. Yeah. So this was an equation that was fitted empirically. So one thing I just wanted to make you aware of with using this expression, we have now an explicit equation for the friction factor, but note that it depends on the flow that's passing through the pipe, right? It still depends on this Reynolds number, which depends on the velocity of the flow. So if you're solving for the flow in a pipe, you'll still need to solve iteratively for that flow rate. The other empirical equations that I'm going to give you don't have this limitation. So they allow you to explicitly compute the flow rate. So I'll talk about each of these in turn. The first approximation that I want to talk about, or the first empirical model for frictional losses that I want to talk about, is the so-called Chezy-Manning equation. In the US, this is generally just known as Manning's equation. And it's used pretty extensively in the field of open channel flow. So you'll see it used a lot in stormwater. Who's heard of Manning's equation, by the way? Oh, yeah, it was in your first lab. I just remember that now. Who's encountered it outside of class? Okay, a couple of you. Anyone working in like stormwater or land development? Yeah. So you'll see this equation a lot. It's used really extensively in the US for open channel flow, but it also can be used for pipes. There's no reason why it can't be used for pipes as well. So it comes from the Chezy equation, which is that same equation that I wrote out earlier that comes from equating the two different expressions for the mean shear stress. So that we have that Q is equal to some coefficient C times the cross-sectional area times the square root of the hydraulic radius times the friction slope. And like I said before, Manning's equation comes from just specifying a value for this coefficient C. So what Robert Manning did back in the 19th century was he took a bunch of studies of open channel flow and fitted a function that related the frictional loss to the discharge for a bunch of different cases. And the expression he came up with for this C coefficient was as follows. So Manning specified from the statistical average of a bunch of studies that this C coefficient can be described well by the following expression. Okay, so we have a coefficient phi, I'll call it phi CM for phi Chezy-Manning, divided by a parameter n that characterizes the roughness, all times the hydraulic radius to the 1/6 power. Okay, so if you take, I'll explain each of these terms in detail, but first I'm just going to take this expression for C and I'm going to plug it back into our Chezy equation here. And this is the form that we will generally see for Manning's equation. So if we take that value for C and plug it back into the first equation on the previous slide, we will get phi CM divided by N as in November times the cross-sectional area times the hydraulic radius to the 2/3 power times the friction slope to the 1/2 power. So let me go through and explain each of these terms. This Q here is the discharge. SF is the friction slope. R is our hydraulic radius. A is the cross-sectional area. And then we have two new parameters here. This N as in November. This is the Manning's roughness coefficient. This is something that you'll look up in a table, for instance, for different values of different materials. And then this phi CM coefficient, this is a coefficient that depends on your units. So the Manning's equation is not dimensionally consistent, so we need this factor here depending on what unit system we're using to ensure that the units works out. And so this phi coefficient takes on different values depending on what unit system you're using. So for SI units, and this is specifically for Q in cubic meters per second, the hydraulic radius in meters, and A in meters squared. So it has to be those units. The phi value is equal to 1. And note that this has some units on it, but they're not important right now. Okay, for US units, and that is discharge in cubic feet per second, hydraulic radius in feet, and cross-sectional area in feet squared. Phi will take on a value of 1.49. And again, this has some units associated with it, but they don't really make any sense and they're not important. So note that your independent variables in the equation need to have these units. Oh, by the way, CMS means cubic meters per second. I got a few questions about that. It's not centimeters, it's cubic meters per second. So this coefficient phi will vary depending on which unit system you're using. If you use SI units, your discharge has to be in cubic meters per second, and the other dimensions have to be in meters or meters squared. Similarly, for US units, your discharge has to be in cubic feet per second. The other dimensions have to be in feet or feet squared. Other units will not work. So Manning's equation, it's widely used in open channel flow. It's also applicable for pipe flow. Note that it is only applicable for water. So there's no information in here about the viscosity of the fluid. That's because Manning's equation really just works for water. And other than that, it's a pretty good approximation and widely used in open channel flow, also in pipe flow. Any questions about Manning's equation? All right, so the next empirical formulation I want to talk about is the Hazen-Williams equation. So this is used pretty much exclusively for pressurized pipe flow, and it's used really only within the United States. It's not used much in other places, but it's widely used here, and it's something you will encounter. So from the Chezy equation, which I wrote out before, we have that the discharge is equal to some coefficient C times the cross-sectional area times the square root of the hydraulic radius times the friction slope. The Hazen-Williams equation gives another form for this C coefficient that is also empirical. So the Hazen-Williams specifies this C coefficient as follows. C is equal to a parameter phi HW, this depends on the units again, times a roughness coefficient CHW times the hydraulic radius to the 0.13 power times the friction slope to the 0.04 power. So if you take this expression for C and you plug it into our general relation between discharge and friction slope, we get the following. This is the Hazen-Williams equation. The discharge Q is equal to our unit coefficient phi HW times our roughness coefficient CHW times the cross-sectional area times the hydraulic radius to the 0.63 power times the friction slope to the 0.54 power. And again, this here is a roughness coefficient, so I'll call this the Hazen-Williams roughness coefficient. And this phi parameter, this is another unit coefficient. So it's a coefficient that depends on your unit system. So for SI units, this phi HW will be equal to 0.849. And for US units, phi HW will be equal to 1.318. So again, for SI units, this means discharge in cubic meters per second, hydraulic radius in meters, cross-sectional area in meters squared. For US units, this means discharge in cubic feet per second, hydraulic radius in feet, area in square feet. So as I mentioned, the Hazen-Williams equation is really used primarily for design of water distribution networks in the United States. It does have limitations in its applicability, just like the Swamee-Jain or Manning's equation have. So in particular, this works for large pipes. So with a diameter greater than or equal to about 5 centimeters. And moderate velocities. And by this, I mean velocities that are less than or equal to about 3 meters per second. So this is really, it's really tuned towards design of water distribution networks, where you'll generally be dealing with larger water mains where water is not moving super fast. Okay, if you're looking at let's say like a chemical processing plant or something where you'll have, smaller pipes and fluids traveling through those pipes, this would not be a good approximation. But this works well for water distribution systems where you're typically dealing with water mains that'll be like 6 to 8 inches in diameter. And note that this also only works for water. It doesn't have any information about the viscosity of the fluid. Okay, any questions about the Hazen-Williams equation and its limitations? Yes.
You can't take the ratio for the different units and like apply it to something else. Like if it was in a non-SI or non-LS unit.
So as long as you're very careful about keeping track of the units for the other terms in the equation, you can apply it to other unit system, but I wouldn't recommend it. Also, you'll almost always be dealing with one of these two unit systems.
And it's unitless, right?
The unit coefficient?
Yeah.
No, it's not unitless. It has some very strange units because we're dealing with quantities raised to a non-integer power. So I'm not writing them down because the units aren't meaningful. They're just used to make the units work out. Good questions. If you're curious, though, you can figure out what these units need to be based on the units of the other expressions. The Hazen-Williams roughness coefficient will be unitless. Okay, good questions. Any other questions about the Hazen-Williams equation or the Manning's equation, their uses and or limitations? Oh, yes.
Is Swamee-Jain the most accurate because we still have to do an iterative process for the Reynolds number?
I would say that Swamee-Jain is probably the most accurate in terms of theory. The thing is that the largest source of uncertainty will not be the equation itself, but rather how well you can specify the roughness parameter. So really the actual accuracy of the equation itself won't usually matter as much as long as you can get the roughness established. And roughness is something that's very difficult to measure directly, so that's often very difficult to do in practice. Okay, good question. Okay, other questions before we move on? So one last thing I want to do before we move on to an example. So we've written all of these equations with the discharge as the dependent variable. We can also re-express all of these in terms of the head loss as the dependent variable. And if we do that, all three of these equations will take the form HL is equal to some coefficient K times the discharge to the M as in Mountain power. So let's take an example for the Chezy-Manning equation. So this is just by example. We have that the discharge is equal to phi divided by Manning's roughness times the cross-sectional area times the hydraulic radius to the 2/3 power times the square root of the friction slope. Okay, the friction slope we know is equal to the head loss divided by the length. So we can re-express in terms of the head loss. We'll get that the head loss is equal to, specifically for a, for a circular pipe, we have that the area is equal to pi d squared over 4. The hydraulic radius, the wetted perimeter is equal to pi d, and the hydraulic radius is equal to d over 4. So if we take this, apply it to a circular pipe and rearrange it for the head loss, we get 4 to the 10/3 times the roughness squared times the length of the pipe divided by our Chezy-Manning unit coefficient squared divided by pi squared divided by the diameter to the 16/3 power, all times the discharge squared. So in this case, if we look at this entire expression, this here becomes K, and this exponent here becomes M. So we can write our Chezy-Manning equation in the form, the head loss is equal to some coefficient K times the discharge to the M power, M is in Mountain. So in this case, M is equal to 2 and K is equal to this whole thing. So for each unit system and for each of our empirical equations, we can write down an equation for the head loss in this form. So let me go ahead and show you what that looks like. If we do that for each of our empirical equations here, we have this nice table of all of our different friction equations. So here we have friction equations expressed in the form frictional head losses are equal to K times Q to the M as in Mountain power. So for Darcy-Weisbach, M is 2. For Hazen-Williams, it's 1.85. For Chezy-Manning, it's 2. And then this specifies our K coefficient for US units on the left and SI units on the right. So this can be a convenient way of expressing these frictional head loss equations. So let's go ahead and do an example applying each of these different empirical equations to computing the flow in a pipe. So let's say we have a horizontal pipe made of cast iron with a diameter of 10 centimeters. Is 200 meters long. And we want to determine the discharge if the measured head, if the measured head loss along that 200-meter section is 24.6 meters. So we're going to apply each of our different equations for the frictional losses and compare the results. First, let's look at Darcy-Weisbach. So let's go ahead and apply Darcy-Weisbach, and let's use that table. So we are in SI units. We're using Darcy-Weisbach. So we'll have a frictional losses in the form H. Our frictional losses are equal to K times Q to the M power. Our M, our exponent, is 2. And our expression for K is 0.0826 times the friction factor times the length of the pipe divided by the diameter of the pipe to the 5th power. So let's write that down. Our head loss is equal to 0.0826 times our friction factor F times the length of the pipe, which I usually call delta X, divided by the diameter to the 5th power, all times Q squared. So M as in mountain, our exponent is 2. We can rearrange this for the discharge. And we get that the discharge is equal to the following quantity: our head loss times the diameter to the 5th power divided by 0.0826 times the friction factor times delta X, bless you, all raised to the 0.5 power. And again, this is something we have to solve iteratively because the friction factor is going to depend on the velocity of the flow, which depends on the flow rate. But we can solve it iteratively, just like we did on Thursday's class. I'm not going to do it here because we've done it a couple times already. But what we'll get is a discharge for the Darcy-Weisbach formulation of 0.024 cubic meters per second. So remember that number. Zero 0.024. Are there any questions? So note that this expression here for the head loss, this is the same as the one we've been using. So this is ultimately the same thing as HL is equal to F times delta X over D times U squared over 2G. These two things are the same. It's just basically I've expanded out all of the constants into this 0.0826 value. And I'm expressing in terms of discharge instead of velocity. So they're the same thing. Just note that sometimes this form here is more convenient to use. Yes. So yes, the roughness height E, I looked up that value to create this answer. Yeah. But the friction factor itself has to be solved iteratively. Yeah. So yes, so for Darcy-Weisbach, the friction factor is not a static constant. It depends on the velocity. Okay, so 0.024 is the discharge that we get from Darcy-Weisbach. Let's go ahead and try Hazen-Williams. So if we go back to our table, So we have SI units and we want to use Hazen-Williams. So we have an equation of the form, our head loss is equal to some coefficient K times Q to the M is in Mountain power. M, our exponent will be 1.85 this time. And our K coefficient will be this expression here. So 10.7 times the length of the pipe divided by the diameter to the 4.87 power divided by the Hazen-Williams coefficient to the 1.85 power. Let's go ahead and write that down. Our head loss will be equal to 10.7 times the length of the pipe, which I'll call delta X, divided by the Hazen-Williams coefficient to the 1.85 power, divided by the diameter to the 4.87 power, times the discharge to the 1.85 power. And we can rearrange this for the discharge just like we did last time. So the discharge will be equal to quantity head loss times the Hazen-Williams coefficient to the 1.85 meters times the diameter to the 4.87 meters divided by 10.7 divided by the length of the pipe delta X. And then we take this entire thing and we raise it to the 0.54 power. Oh, sorry, that was not written very neatly here. 0.54. So that's 1 divided by 1.85. So let's go ahead and try to compute this. I'll call this QHW for the discharge computed from the Hazen-Williams equation. So what is our head loss from the problem statement? 24.6 meters, very good. Okay, our Hazen-Williams coefficient, we don't know it yet. So I'm just going to leave this blank, but I'll write it as CHW. The diameter was 10 centimeters, so that's 0.1 meters to the 4.87 power. And this is all divided by 10.7 times the length of the pipe, which was 200 meters. We're going to raise all of this to the 0.54 power. So we need to specify this Hazen-Williams coefficient. If I remember correctly from the problem statement, we have that the material of the pipe is cast iron. So what I'm going to do is I'm going to open up a table of Hazen-Williams coefficient, and we're going to try to figure out what the right coefficient to use is. So let's go ahead and go to our reference tables. You'll see that there's a table here called Hazen-Williams coefficients. So let's open this up. Okay, and we have cast iron. So note that the Hazen-Williams coefficient varies quite a bit for cast iron. So for new cast iron, it's going to be about 130. For 10-year-old cast iron, it varies from 107 to 113. And then for 40-year-old cast iron, it's going to be 64 to 83. So just based on these descriptions here, does a lower Hazen-Williams coefficient correspond to a more rough or less rough pipe? More rough. So the lower the Hazen-Williams coefficient is, the more rough the pipe is. So this is quite a range. I'm just going to select from the lowest point to the highest point of this range as our values for the Hazen-Williams coefficient. So 64 to 130. So our Hazen-Williams coefficient is in the range of 64 to 130. And if we use these values for the Hazen-Williams coefficient, we can explicitly compute the discharge. So no need to solve iteratively here. The Hazen-Williams coefficient does not require any information about the velocity or the discharge. So we can solve explicitly for the discharge. And we get that our discharge is between 0.013 cubic meters per second and 0.027 cubic meters per second. So which one of these values corresponds to the larger roughness? Which corresponds to the rougher pipe? The smaller value or the larger value? The smaller value. So the greater roughness, the greater head losses there are, and the smaller the discharge will be. Yes.
Or like 37.
Yeah. I would give you clear instructions on what to do in that case. Because I don't, that seems like a reasonable approach, yeah. But yeah, I would give you clear instructions on what to do. Okay, other questions? All right, so that's the Hazen-Williams equation. You'll note that there's a very large range of potential discharge values. So 0.013 to 0.027. This larger value is about twice that of the smaller value. So our results are really sensitive to those estimates of the roughness. If we compare it with our first answer, we see that the discharge is closer to the upper range of the values we got from the Hazen-Williams expression. Okay, so let's take a look at Manning's equation. So this will be our last one. So if we go back to our table of friction equations, we have that for Manning's equation, our friction losses can be expressed in the form H is equal to K times Q to the M, where our M as in Mountain exponent is 2, and our coefficient K is equal to 10.3 times the roughness squared times the length of the pipe divided by the diameter to the 5.33 power. So let's write that down. Our head loss is equal to 10.3 times the Manning's roughness squared times the length of the pipe divided by the diameter to the 5.33 power, all times Q squared. We can rearrange for Q just like we did before. So Q under the Chezy-Manning equation is equal to quantity head loss times the diameter to the 5.33 power divided by 10.3 times the roughness squared times the length of the pipe, all raised to the 0.5 power. So let's go ahead and substitute values. We have that our discharge from the Chezy-Manning equation is equal to, our head loss is equal to 24.6 meters, just like before. Our diameter is 0.1 meters, just like before, raised to the 5.33 power. We're going to divide by 10.3 times our roughness squared times the length of the pipe, which is 200 meters, and we're going to raise this entire expression to the 1/2 power. So just like before, we have to look up values for the Manning's roughness. So this is cast iron pipe. We can go, I'll give you a second to finish writing this. We'll go back to our lookup tables just like before. So if we go to our lookup tables, we have table 3.3, Manning's N coefficients. And we can go down. So we have different Manning's roughness values, their minimum and maximum value for different materials. And we'll see that for cast iron, our Manning's roughness is going to be 0.011 to about 0.015. Okay, so note that for Manning's roughness coefficient, a larger roughness coefficient means more rough. So the Hazen-Williams coefficient is the only one where a smaller value means more rough. For Manning's equation, larger value means more rough. Okay, so our roughness is in the range of 0.011 to 0.015. We take those values and plug it into our expression. Again, we can compute explicitly for the discharge. We don't need to solve iteratively. Oh, sorry, this is a range. So we'll find that our discharge is between 0.016 cubic meters per second and 0.022 cubic meters per second. And if we compare with our answers from before, you'll see that we get values that are a little bit lower than those under the Hazen-Williams coefficient. At the upper range, we're close to our answer computed under the Darcy-Weisbach equation. But again, our results are really sensitive to the selection of those roughness parameters. So like I mentioned before, usually the roughness parameters are the largest source of uncertainty. They contribute more uncertainty than the selection of the equation itself. So basically, in most cases, it doesn't really matter which equation you use as long as you nail down those roughness parameters accurately. Are there any questions about the different empirical equations for frictional losses? Any last questions? Yes?
So the only one that we have to like iteratively solve for is the first one. The other two do.
Yes, the only one you have to iteratively solve for is Darcy-Weisbach, because the friction factor depends on the velocity. Yes. And for problems on homework and tests, I will tell you which equation to use. So you don't have to, select which equation to use. I'll tell you explicitly what formulation to use. Yes.
So does empirical just mean like experimentally tested?
Yeah, so it means generally derived from data. Yeah. There are some equations that are semi-empirical, so they, are theoretically based, but the coefficients are derived from data rather than from theory. But some equations are just completely empirical. Yes.
Did we get it Hazen-Williams given the diameter is not very like oh yeah, never mind. That's the 5 minutes.
So yeah, so again, if it's for a problem, I'll tell you which equation to use, unless it's some sort of multiple choice question where I'm asking, is this equation valid for this type of pipe and flow rate? But otherwise, if it's for a longer problem, I'll tell you what to use. Good questions. Any other questions? Okay, so you know what? We're getting into minor losses next, and I don't have a whole lot of time left in the class, so I'm just going to let you out early. And I will see you on Thursday. We're going to talk about minor losses, and we'll basically be finishing up module 1 on pressurized pipe flow.